Today we're going to talk about compound events with probability. And compound events are just events that combine two or more simple events. So we're going to do some examples of this. First of all, consider the difference between these two. What is the probability of choosing a king and a jack compared to what is the probability of choosing a king or a jack? Well, obviously, the difference here is the and became an or. Let's think in terms of what the difference is, what that means. Choosing a king and a jack implies we're picking two cards. One is a king and one is a jack. We're choosing a king or a jack implies we're picking one card and it's either a king or a jack. This and this or idea end up being very important in probability, and that's what we're going to talk about today, how to handle and problems and how to handle or problems. Let's start with and problems. There's two situations that can occur where they're independent of each other or where the probabilities are dependent on each other. Let's look at the independent case first. Okay, our example, we're going to roll a die, a six-sided die, and we're going to flip a coin. So A is the probability the die is a 4, and B is that the coin is on tails up. So we want the probability of P and A. Well, here's the rule. The rule is when and is involved, we multiply the two probabilities together. So the probability that when we roll a die, a 4 is face up, well, there's 1 4 out of the 6 sides, so that's a 1 in 6 chance. Just like the probability of rolling a 5 would be a 1 in 6 chance. The probability that the coin is a tail, well, that's 1/2. Because this was an and problem, we are going to multiply the two together. So that is a 1 in 12 chance that we roll a 4 and flip a coin and get a tail. So and always means multiply. Okay, let's look at where the events are dependent on each other and talk about the difference. Once again, we are still talking about and problems, so we are still going to work with multiplication. A jar contains 5 red marbles, 3 green, and 2 blue. We're picking 2 marbles without replacing the first before we pick the second. Find the probability the first marble is red and the second is green. Okay, well, what's the probability the first marble is red? Well, there's 5 red marbles, and there's a total of 5 plus 3 plus 2. There's a total of 10 marbles. So 5 out of those 10 marbles are red. And the probability the second marble is green. Well, there's 3 green marbles out of how many? Well, we have one of those marbles in our hand now. So there's only 9 marbles left in the jar. So 3 out of those 9 marbles that are left are green. This is where the dependent part comes on. This probability, the second probability, changes to 3/9 because of what happened first. So these are dependent. The second probability is dependent on the first. Well, I could reduce first and then multiply to save myself some work. I have a 1 in 6 chance of first picking out a red and then reaching in and picking out a green. Once again, the important thing to remember here is and means you're going to multiply. Let's look at the or case. Okay, or implies that we're going to have an addition involved. We're going to look at 2 situations, one where A and B are what we call mutually exclusive events, and then non-mutually exclusive events will be our second possibility. Okay, we're drawing a card from a deck. What's the probability you draw a 10 or, once again that or word, a king? Now, why these are mutually exclusive events is you can't have a card that is both a 10 and a king. It's either a 10 or it's a king. There's no overlap. So we say those are exclusive of each other. They're mutually exclusive. Okay, let's review what a deck of cards looks like. So we have 4 suits, clubs, diamonds, spades, and hearts. And in each suit, there are 13 cards. There are the 3 face cards, a king, a queen, and a jack. Those are the face cards because they have faces on them. And then we have the numbers 10 down through 2. And then we have the ace, which is like a 1. And we have that for every suit. So there's 13 clubs, 13 diamonds, 13 spades, and 13 hearts. So the probability that we pick a 10, well, there's a 10 of each suit. There's a 10 of clubs, of diamonds, of spades, and of hearts. So there's 4 10s out of the total of 52 cards. The probability that it's a king, once again, there's a king of clubs, of diamonds, of spades, and of hearts. So 4 out of the 52 cards are kings. It's an OR problem, so I'm going to add those probabilities up. That gives me 8 out of 52, which reduces to 2 out of 13. So the chance that I either pick a 10 or a king from a deck of cards is a 2 out of 13 chance. Non-mutually exclusive means there is some sort of overlap. So let's consider the deck of cards again. What's the probability that we pick a 10? Well, how many 10s are there? There's 4 out of the 52 possible cards. Okay, it's still an OR problem, so we're going to add. What's the chance that it's a diamond? Well, remember what we said, each suit has 13 cards in that suit. So the chance that it's a diamond is 13 out of 52. Now let's deal with this non-mutually exclusive part, this overlapping part. What do we have an overlap with 10s and with diamonds? Well, the 10 of diamonds. We counted the 10 of diamonds here. It's one of those 4, and it's one of those 13. So we counted it twice. We overlapped it. So we have to subtract off one of those because we don't want to count the 10 of diamonds in both categories. So this is the non-mutually exclusive part. We have to add on that step of subtracting off the overlap. That's 17 minus 1, 16 out of 52, which reduces to a 4 out of 13 chance of picking a 10 or a diamond. So let's try a couple of examples. 2 marbles are drawn without replacement, and that's important. That means the events end up being dependent on one another. From a bowl containing 7 red, 4 blue, and 9 yellow marbles, what's the probability that both are red? So I am looking for the probability that the first one is red and the second one is red. It's an and problem. Remember what we do with and problems? Yeah, we multiply and problems. So the probability the first marble is red. Well, there's 7 red marbles. Let's see, how many total? We've got 7, 4, that's 11, and 9. There's 20 marbles in all. So 7 out of the 20 are red. What's the probability that when we reach in, the second one is also red? Well, how many red marbles do we have left? Yeah, there's only 6. One of them is in our hand. So 6 of the remaining marbles. And how many are remaining? 19 are remaining. So we have now a 6 out of 19 chance that the second marble is going to be red. Because it's an and problem, we multiply. That gives me 42, 7 times 6, out of 380, 20 times 19. That reduces to 21 over 190. Sometimes it's helpful with probability if we put this as a percentage instead of a fraction. This ends up being approximately 11% of the time when we reach in and both marbles we pick are red. Okay, for B, what's the probability that neither is red? So the first one is not red and the second one is not red. Okay, so let's talk about how many not reds are there. Well, there's 7 reds, so there are 13 marbles that are not red. So 13 out of the 20 marbles are not red. Now we're going to reach in and pick another marble out. Well, how many now are not red? Well, we have 1 in our hand, so now 12 out of the remaining 19 are not red. 13 times 12 is 156. 20 times 19 is 380. This once again reduces. Or I could find out what 39 divided by 95 is. It ends up being about 0.41 or 41% of the time. So when we reach in and pick these two marbles out, 41% of the time, the marbles will both be not red. They'll be blue or yellow. And then we have C. What's the probability that at least one is red? Well, here's the probability that none of them are red. So the probability that at least one is red is the probability that both are red, plus the probability that the first one is red and the second one's not, or the first one is not and the second one is red. So there's actually 3 cases to consider here, or there's an easier way around this. If 41% of the time neither one of them is red, then 59% of the time, at least one of them has to be red. So out of the complete 100% of the time, if 41% of the time neither's red, what's left over? 59% of the time, at least one of them must be red. We're going to pause here and we will start another video with the remaining problems.